You know, when you look at a mirror, do you ever really think about what's going on? It seems so simple, right? But the world of light and reflection is actually jam-packed with these amazing secrets hiding right in front of us. So today, we're going to pull back the curtain and uncover them. Let's get right into it.
Okay, so you've definitely seen mirrors like these, right? At a carnival or a science museum, you look in one and suddenly you're a giant. The next one makes you super short and wide. And then there's the one that flips you totally upside down. It's hilarious for sure, but guess what? It's pure physics in action.
And really, that's the big question we're tackling today. Why do some mirrors just lie? How come your bathroom mirror gives you a straight-up reflection, but these other ones warp reality in all these weird and wonderful ways? Well, stick around, because we are about to find out.
So, to crack this code, we're going to start with a few optical puzzles you probably see all the time, maybe without even noticing. And believe it or not, the key to solving them, well, it might just be sitting in your kitchen drawer right now.
Okay, here's a perfect example. We've all been there. You're driving, you glance in your rearview mirror, and you see an ambulance coming up behind you. But wait a second. Why is the word ambulance written completely backwards on the front of the truck? I promise you, it's not a typo. It's actually a super clever trick using physics.
The secret is something called lateral inversion. Basically, a normal flat mirror flips everything horizontally. Left becomes right and right becomes left. So by printing the word in reverse on the ambulance, your rearview mirror does the work of flipping it back the right way. That way, the driver in front can read it instantly and know to get out of the way. So simple, but absolutely brilliant, right?
Now this is where it gets really interesting. Remember that thing in your kitchen drawer? I'm talking about a spoon. A simple, shiny spoon is basically a mini science lab. It's two different kinds of curved mirrors in one. Go ahead, grab one. Look at your reflection in the part that holds the soup. Now flip it over and look at the back. Totally different, isn't it? Okay, so before we totally decode the spoon mystery, we have to cover the basics. And here's the amazing part. It turns out that every single reflection in the entire universe, I'm talking everything from your bathroom mirror to those wacky funhouse mirrors, even the reflection in a single drop of water, they all follow just two super simple, totally unbreakable rules. To get these rules, we first got to meet the players in this game of reflection. First, you've got the incident ray. That's just the beam of light coming in and hitting the mirror. Then you've got the reflected ray. That's the light that bounces off. And finally, the normal. Now, the normal sounds fancy, but it's just an imaginary line we draw straight out from the mirror at a perfect 90-degree angle right where the light hits. It's basically our referee, our point of reference.
And here they are, the two laws. Ready? Law number one. The angle the light comes in at is always equal to the angle it bounces off at. We call it angle I equals angle R. No exceptions. Law number two. The incoming light, the bouncing light, and that normal line, they all lie on the same flat plane. Imagine you could just lay a sheet of glass over them and they'd all be touching it. That's it. Those are the two rules that run everything.
All right, let's do a quick pop quiz. This is a classic trick question, so pay attention. If the total angle between the incoming ray and the reflected ray is 40 degrees, what's the angle of incidence? Think back to that first law. Did you get it? The answer is 20 degrees. See, that total 40-degree angle is made up of two equal parts, the angle of incidence and the angle of reflection. So you just have to split it right down the middle. 40 divided by 2 is 20. Simple as that.
Okay, so now we get the rules for flat surfaces. Easy enough. But what about our funhouse mirrors? What about the spoon? What happens when the playing field isn't flat anymore? Well, this is where it gets fun, because the rules don't actually change. But the results, they change a lot. So first, let's tackle a quick question. Why can you see a reflection in a mirror, but not on, say, a wall or a piece of paper? I mean, both are reflecting light, right? The difference is smoothness. A mirror is super smooth, so when parallel light rays hit it, they bounce off in a nice, orderly, parallel way. That creates a clear image. But a piece of paper, even though it looks smooth, is actually really rough on a microscopic level. So when light hits it, the rays scatter in a million different directions. And here is the mind-blowing part. Every single one of those scattered rays still perfectly obeys those two laws of reflection. It's organized chaos. Okay, let's get back to our spoon. The inside of the spoon, the part that curves inward, that's a concave mirror. It focuses light, or converges it. This is why your reflection looks weird and why dentists use tiny versions of these to get a magnified look at your teeth. Now, the back of the spoon, the part that bulges outward, that's a convex mirror. It does the opposite. It spreads light out, or diverges it. And you see these everywhere, like on your car's side view mirrors.
And that brings us right to that famous warning, objects in mirror are closer than they appear. Now you know why, because that convex mirror is spreading the light out. It lets you see a huge, wide-angle view of the road behind you, which is great for safety. But the trade-off, the catch, is that it also shrinks the image, making cars look smaller and farther away than they really are. All right, so we've talked a lot about mirrors, which reflect light. But what about things that light passes through, like a window or a magnifying glass? Well, it turns out the most incredible, most sophisticated optical instrument ever known isn't in some high-tech lab or a giant telescope. It's literally sitting inside your head.
Seriously, your eye is like a ridiculously advanced camera. Here's the quick tour. Light first enters through the cornea, that clear outer layer. The colored part, the iris, controls the size of the pupil, letting more or less light in. Then the lens behind it does the fine-tuning, focusing that light perfectly onto the retina, which is like the sensor at the back of the eye. From there, the optic nerve zaps those signals to your brain, which magically turns it all into the picture you see.
And that sensor, the retina, is amazing. It has two different types of light detectors, like two specialized teams. You've got the rods, which are your low light specialists. They're super sensitive, but they can only see in black and white. Then you have the cones, your daytime team. They need a lot of light, but they're the ones that detect color. And this totally explains why it takes a minute for your eyes to adjust to a dark room. You're basically waiting for your rod team to power up and take over.
So, we know light can bounce, but that's not its only trick. It can also bend, and it can even split apart into a rainbow of colors. And these two abilities are responsible for, well, pretty much everything, from the most beautiful things in nature to the technology we literally can't live without.
You've all seen this, right? When a beam of white sunlight hits a glass prism, it magically splits into all the colors of the rainbow. That's a process called dispersion. What's happening is that as the light enters the glass, each color gets bent just a little bit differently. Think of it like a race where each color runs at a slightly different speed, causing them to spread out and show us that beautiful spectrum. And the most spectacular, most famous example of dispersion in the world? A rainbow, of course. A rainbow is basically a giant temporary prism made of millions and millions of tiny little raindrops floating in the air. Each individual droplet bends and splits the sunlight, and all together they create that incredible arc of color across the sky. Now, that bending of light has its own name, refraction. And refraction is the magic behind lenses. And hey, does this sound familiar? Just like with our curved mirrors, lenses basically come in two flavors. A convex lens, which is fat in the middle, brings light together, or converges it. And a concave lens, which is skinny in the middle, spreads light out, or diverges it. And once you know this, you see it everywhere. The glasses on your face that help you see clearly, they're bending light. The incredibly complex stack of lenses inside your smartphone camera, all about bending light with precision. Microscopes, telescopes, binoculars, they're all masters of refraction.
So there you have it. From the simple reflection in a spoon to a massive rainbow stretching across the sky, these basic principles of light are constantly and quietly shaping our entire world and how we see it. So here's my challenge to you. The next time you look in a mirror or catch a reflection in a puddle or use the camera on your phone, just stop for a second. Now that you know the rules of the game, what other secrets can you find hiding in the light?